Okay, in this video we're going to finish up talking about quadratic functions and their graphs, and I want to just remind you this about what the domain and the range of our graphs are. So remember, the domain of a function is the set of all possible input values, and the range is the set of all possible output values. So remember, when you're thinking input values, I want you to think x values. And when you're thinking output values, I want you to think your y values. Okay, so when you're thinking about the domain and the range, it's sometimes helpful to think about, well, what x values can I put in for this graph? And remember, these graphs go on forever in both of these directions. And so, well, are there any x values that you could not have? I could have this one would keep going on way up here. I could figure out this one here, way up here. So your domain for this function, or this graph, is going to be all real numbers. But it's your range value that does become restricted, because when you look at where your y values are, notice that this being your smallest point on your graph corresponds to y equals -2. That's as small as it goes. There's never a point where y is going to be -3 or -4 or -5 or so on. So the range values for this function are based off of that minimum point, and so all of your range values are going to be y bigger than or equal to -2. Similarly, your input or domain values for this function, again, it's all reals, and I'll give you a hint. For a quadratic, it's always going to be all reals for your domain. But what about your range? Well, this one has a maximum point. So that's the highest y value that you're going to get. So your range for this will be all reals less than or equal to 4. This one again was greater than or equal to -2. This one is less than or equal to +4. So your range values actually play off of your maximum or minimum, i.e. your vertex point. So what you have to figure out is, if it opens up, remember it has a minimum. If it opens down, remember it has a maximum. So that's going to be based off of your a values. So let's consider this function, 4x squared minus 24x plus 88. Well, this has a positive a value, so it opens up, so it's going to be like this one and have a minimum value. Okay? And so then we're going to find that minimum value by doing the negative b over 2a piece here. So this is going to be negative 24 over 2 times 4. So this becomes 24 over 8, which is 3. Now that's not enough. I actually have to figure out, well, what is my function at that 3 value? So 4 times 3 squared minus 24 times 3, and then plus 88. So this becomes 3 squared is 9, 9 times 4 is 36. 24 times 3, well, that's 72, so minus 72, and then plus 88. So 36 minus 72 is a -36 plus 88. So -36 plus 88 is going to give me 52. So my minimum point, that smallest point, is going to happen at 3, 52. So the last thing it wants you to do is domain and range. Remember, again, your domain is going to be all real numbers. It's going to be that time every time you're working with parabolas. Okay? But your range value, remember, it's based off of your maximum or minimum. Well, in this case, it's a minimum, so it's always going to be greater than or equal to whatever your smallest y value is. So in this case, it's 52. So we're going to say all reals y greater than or equal to 52. That's how we can write that. All real numbers y greater than or equal to 52. Or you could say all y greater than or equal to 52. There's a lot of different ways you can say it. Okay? And then, of course, sometimes it's helpful to figure out a maximum or minimum of an application problem. Okay? So let's take a look at these. This one says, among all pairs of numbers whose sum is 20, find the pair whose product is as large as possible. What is the maximum product? So let's talk about pairs of numbers whose sum is 20. So x plus y equals 20. And then we say we want their product to be as large as possible. I'm going to use P for product. Product is equal to x times y, right? But here I'm dealing with x's and y's and x's and y's, and so I want to be dealing with just one of them, x's or y's. So I'm going to go ahead and solve for x here. And I'm going to say x is equal to negative y plus 20. And then I'll plug that in for x here. So now my product is equal to negative y plus 20 times y, or negative y squared plus 20y. This is my product. Notice it's a quadratic, okay? If you were to graph this, would this open up or would it open down? Look at that a value. It's negative. This would open down. So it's going to have a maximum, which makes sense because the problem asks for a maximum product. Okay? So to find that, we need to find that vertex point. So we need to do the negative b over 2a piece. So this is going to be negative 20 over 2 times negative 1. So negative 20 over negative 2 is 10. So this is going to give me a maximum when y equals 10. This is going to be my maximum point, right? So if y equals 10, well then, what does x equal? Think back to here, x plus y equals 20. So x also has to equal 10. So your max product would be 10 times 10, which is 100. The hardest part here was getting set up with that quadratic equation, so then we could find the vertex of it. Okay? Let's talk about this next one. You have 90 yards of fencing to build a rectangular dog pen. So I'm going to draw myself a little rectangle here. Okay? Find the dimensions of the rectangle that will maximize the enclosed area. Again, maximize is what we're looking for. So when you have a dog pen, you have a length and you have a width, right? And I need to do something with this 90. It says I have 90 yards of fencing, excuse me, and that's got to go all the way around. Well, remember, that's our perimeter. But to find the perimeter, I take 2 of my widths plus 2 of my lengths, and that has to be my perimeter, which is 90. Okay? And I want to maximize my area, and area is equal to length times, not plus, excuse me, times width. So what I'm going to do over here is I'm going to solve for L. And I get 2L equals 9D minus 2W. When I divide by 2, I get L equals 45 minus W. Plug that back in over here, and I now have 45 minus W, so minus W, times W, or my area is equal to, if I rewrite this in standard form, negative W squared plus 45W. Notice again, this is a quadratic. Notice again, the a value is negative, so it's opening down, which is good because we want to find a maximum. So we do the negative b over 2a piece, which is negative 45 over 2 times negative 1. So what I'm really doing is 45 divided by 2. They're both negative, so that gives me 22.5. So when W equals 22.5, I'm going to have that maximum. Well, if I plug that back in, I can figure out what my L is. So this gives me 45 plus 2L equals 90. When I subtract, I get 2L equals 45. Huh, interesting. L equals 22.5 also. So it says find the dimensions of the rectangle that will maximize the enclosed area. I will have a width of 22, oops, you know what I'm missing there? 22 yards. And I will have a length of 22 and a half, and I will have a length of 22 and a half yards. So when you're doing these application problems, the first thing that you have to really do is you have to get set up with a quadratic. So use what you know, substitute in, and you'll end up with a quadratic. If you're looking for a maximum, the a value should be negative in case it was in both of these times. So then you find that vertex point, because the vertex is either your maximum or your minimum. Solve that out, and you should be able to find either your missing dimensions like it was here, the missing numbers like it was here, and then that can give you. I might ask you, what is the maximum area? Well, then you would actually have to go back and multiply your 22.5 times your 22.5, and you would find that your maximum area would be 506.25 square yards. Remember, yards times yards, square yards. Okay? All right, that's all for this one. And that's all for section 10.4. We'll see you next time. Keep up the good work.